G'day chemistry students, welcome to the second last module in the HSC course. In this module we'll be looking at all things organic chemistry. To start in this first video we are looking at dot point 7.1.1. We're just looking at some of the basics of being able to construct and draw organic substances. This is going to give us a lot of tools to be able to use for the remainder of the module. Let's get into it. What I would like to look at first are a few samples of organic chemicals. All of these five guys here are classed as organic chemicals and should be quite familiar to you. Ethanoic acid is down the bottom here. That's essentially vinegar. We've also got a molecule of glucose, which is a simple sugar, and methane as well, which you may be familiar with also. Possibly you've heard of capsaicin. Essentially, this is the molecule that is responsible for the spicy flavors in a bunch of spices, namely chilies. We also have vanillin, which is the chemical that gives vanilla its distinct flavor. Now, what we should be able to notice is that there are some common themes that run through each of these chemicals. Firstly, we should see that there are a bunch of carbons that run along each of these chemicals. Carbons form the skeleton of all organic molecules. I'll note as well that for all these intersections on the glucose, they are all actually carbons as well. They're just using a little bit of a different system to draw the structure. And there are lots and lots and lots of carbons. And most of those carbons are surrounded by a bunch of hydrogens. These hydrogens also form a major part of organic molecule structures. We may also see other elements, namely oxygens are present in most of these chemicals. We may also see some nitrogen. So when we look at these organic molecules, we're mostly looking at structures that have carbon and hydrogen. Possibly there are some oxygens and nitrogens, and they're actually the things that make the chemicals the most unique and interesting and give them their different characteristics. To be able to understand how to draw organic structures, we have to have a really strong foundational idea of covalent bonds and how they form. And to explain that, I'm going to do a little bit of quick revision on some stuff that we looked at in Module 1 around electron orbitals. You should recall seeing some images like this that represent a bunch of different orbitals, S, P, D, and F orbitals here. Essentially, these orbitals are geometric shapes, which show areas in which electrons can exist. Each geometric shape that we can see here has the capacity to hold 2 electrons each, and these zones increase in volume as the energy levels increase. So for example, we could have a 1s orbital that could be quite small, but as we go up an energy level, a 2s orbital could be larger. Generally speaking, for most chemicals, we focus a lot on the S and P orbitals, especially when we're looking at organic chemistry. We're not actually working with chemicals which are big enough to have D and F orbitals, so I'm going to be focusing on our top two. So our S orbitals are spherical in shape, whereas our P orbitals have a pair of nodes that run along one of our 3 axes for our 3 dimensions. So our Px, Py, and Pz orbital. These are the guys that participate in organic bonding. What we should also note is that organic molecules covalently bond, and that in some cases, there may not just be single bonds, but what we call double and triple bonds. A quick reminder that a line between 2 elements represents a bond. One of these covalent bonds essentially is 2 electrons that are being shared between the 2 elements. So if we have a double bond, there are 2 pairs or 4 electrons being shared between the 2 elements. For a triple bond, there are 6 electrons being shared in 3 lots of 2. So when we are looking at organic molecules forming bonds, a lot of the time what we see is an overlapping of orbitals. So essentially a pair of orbitals where one side of the orbital begins to overlap, enabling sets of electrons to be able to sit in the middle and then be shared amongst the 2 atoms. So we may have an overlapping of s orbitals, might look something like this. Another representation is over here. We may have an overlapping of p orbitals. These 2 orbitals, when they overlap, make a shape in which the central nodes get larger and the outer nodes get smaller. The electrons can exist here, and that helps to form the bond. So when we're looking at bonds like this, we are forming something called a sigma bond. With this sigma bond, we have orbitals directly overlapping over the top of each other. Really, they may just inflate in size. And these bonds are really, really, really strong. We can also have something called pi bonds, and this is for where our p orbitals don't line up with each other exactly. So if we look back, these p orbitals, say, might be px orbitals. They exist along the axis of the same dimension. Whereas for these p orbitals, these might be py or pz orbitals, where they do not directly line up. And so what we see is that for those, say, py or pz orbitals, is that they don't directly overlap on top of each other. There's a gap in between, and that makes it a little bit difficult for that bond to form. What the two orbitals can do, though, is move in towards each other and begin to overlap. And this is sort of what we see as a result at the end. Now, these pi bonds can also form, can have two electrons being shared within this orbital space. But because the p orbitals had to contort themselves so much, these bonds are significantly weaker than the sigma bonds. So what we'll see always is if we're forming a single bond, it's always going to be a sigma bond. If any additional bonds are being formed between organic elements, then they will be forming pi bonds. So if I have a double bond, like this one here, it would be made up of one sigma bond and one pi bond. If I formed a triple bond, it would be formed of one sigma bond and two pi bonds. If I only had a single bond, it would just be the single sigma bond. Keeping in mind too, as I said before, the sigma bond is significantly stronger than any pi bond. That's going to have a little bit of impact later when we start talking about chemical reactions. So if carbon is number 6 on the periodic table, that means that it has 6 electrons, and its electron configuration is 1s2, 2s2, 2p2. When we're looking at filling up our orbitals, we know that its first one is full. There's only 2 electrons in the first orbital. The second orbital is composed of the 2s and 2p sets. And we know that to make carbon a stable element, we need to fill up the 2s and the 2p orbital. What that means is we need an extra 4 electrons. There are 6 electrons in every p orbital. That's because of our px, py, and pz orbitals, each having 2 electrons each. So 2 plus 2 plus 2 is equal to 6 electrons. So that means we want an extra 4. Now, to get those extra 4 electrons, what a carbon does when it's forming an organic molecule is make 4 separate covalent bonds. So if it forms all these bonds and bonds onto something else, maybe let's say for argument's sake it's hydrogen, then what it has been able to do is attain 8 electrons, become fully stable, and end up forming a full organic molecule. This, as we saw before, is methane. And what we see that is the most important is that carbon needs to form 4 bonds to become energetically stable. It's a little bit different for hydrogen though. Hydrogen is the first element on our periodic table, and it just has an electron configuration of 1s1. Now, to be able to fill that s orbital, we just need 1 more electron. If we need 1 more electron, then what we expect is to only need 1 covalent bond. So it can form a bond with something else. In this case, let's just say that it is a carbon. Then the hydrogen would be stable and all good. Looking at our oxygens, what we can see is that there are 6 outer electrons. That's got to do with its total number of electrons and its electron configuration, which is 1s2, 2s2, and 2p4. Now the oxygen only needs 2 additional electrons, which means that it will end up forming 2 bonds with other substances. In fact, that explains what happens when it bonds with hydrogen to form water. And for our final element, the electron configuration for nitrogen is 1s2, 2s2, 2p3. Now, to completely fill up the p orbital, we need 3 more electrons, which means 3 more bonds need to be formed to end up getting a total of 8 for our s and p electrons. And this actually forms ammonia if the nitrogen bonds to all the hydrogens. So in summary, carbons have 4 outer shell electrons to start with, which means it needs 4 extra bonds to make 8. Hydrogen has 1 outer shell electron and only needs an extra 1 to get to that 2. For oxygen, it's got 6 electrons to start with, just needs 2 more to make 8. And for nitrogen, there are 5 electrons that we start with, but there needs to be 3 bonds formed to make 8. What we'll do in our first lesson is do a bunch of practice constructing molecules and drawing some of these diagrams so that we can get our heads around how to construct a bunch of different organic molecules. Something else that we'll focus on is displaying organic molecules in a few different ways. So we can show or communicate to readers what kind of organic molecule we're working with by just giving simply a molecular formula. We could also show an empirical formula, so the lowest ratio of each of the elements in the substance. So everything here is just being divided by 2. We could represent this same molecule using a condensed formula, so we can show each of the groups that are bonding. A displayed formula shows all bonds for all elements. The structural formula is very similar to the condensed formula in the sense that all of the hydrogens are grouped to each carbon or oxygen, but the bonds are still being shown between all other elements. We can also show a skeletal formula of these molecules, essentially here not writing down any of the carbons or hydrogens. One of these intersections represents a carbon if it's not been labeled as anything else. We just sort of have to fill the gaps in our own heads. Each of these representations has its sort of own time and place. For example, the skeletal formula really distinctly highlights functional groups, the parts of chemicals that aren't just the carbon chain. And these are the things that are usually some of the more interesting parts or show things the most clearly. So there's a lot of times where the skeletal formula sort of keeps everything clean and very direct about some of the more important parts of the molecule, whereas sometimes using something like a displayed formula can be really important when looking at factors where the carbon chain does come into play. Thank you very much, everyone. In the next video, we're going to start looking at a bunch of naming rules. The systems that are in place to name organic chemicals can be quite complex, so we're going to break it up in a few videos and do a bunch of practice in class. What we're going to be looking at first is naming carbon chains, not focusing on some of those functional groups that I just outlined previously. But until then, have a good one.